Okay. In the last lecture class, we introduced the idea of light as an electromagnetic wave. In today's lecture class, we're going to examine some of the characteristics, the properties, features of light. In particular, in today's lecture class, I want to go through these three items. I've just got to get my pen working again here. I want to say a little bit about what we call the dual nature of light. So by dual nature of light, we mean that light exhibits both particle-like and wave-like characteristics. And I'm just going to give you a little bit of an introduction and history to this dual nature of light. We'll then get on to more quantitative work. And we're going to talk about reflection of light. That's a fundamental property of light. We're going to talk about the law of reflection, and we're going to look at some examples, illustrations of reflection. And then we're going to do the same thing for what we call refraction. Refraction is the bending of light rays. We're going to talk about the law of refraction, and we're going to look at some examples and illustrations of the law of refraction. And so this is basically our content for today. Mostly ideas in item number 1, and then getting a bit more rigorous, a bit more mathematical, a bit more quantitative in items number 2 and 3, in the items on reflection and refraction. Okay, so nature of light, and really I'm meaning this dual nature of light, which is a really strange, peculiar, weird concept. We think of things as being either particles or waves. So if I think of the ocean, I think of water waves. I think of sound, I think of sound waves. If I think of, a football or a basketball, I'm thinking of sort of particles, objects. But light actually exhibits both particle-like properties and wave-like properties. So let's take a look at that. There's a long history, and I would love nothing more than spending the next few hours just discussing it with you. But I've forced myself to keep it on just a couple of slides here. A long history of arguments about whether light is particles, there's like particles of light, or light is waves. There's like a wave or a stream of light. And these arguments go back to 2 scientists that we've met, one in 2011, Isaac Newton. I'm sure you remember him. I mean, in the sense that you remember what we discussed about him. And then there's James Clerk Maxwell. And I'm sure you remember him because we've been talking about him in the last class. Again, he's not around now, but we remember his work. So Isaac Newton explained light as being a stream of particles. So there's little particles of light. And he explained the reflection and the refraction of light with this picture that light was a stream of little particles, stream of tiny particles. So in the history of light, understanding of light, that was a accomplishment and an idea that light was particles. As we met last class, right, James Clerk Maxwell explained light as actually a wave. a wave of electric and magnetic fields that are kind of self-sustaining, self-propagating, and carry energy and carry momentum and travel at a certain characteristic speed. And so these were two theories, two opposite theories that emerged over the last centuries about the nature, the characteristics, the properties of light. That light's particle-like and light is wave-like. Now, those were theories about light being particles or light being waves, but there are also plenty of experiments to examine whether light showed evidence of being particles or light showed evidence of being waves. And what happened in the history of investigating light is what emerged was evidence for both wave-like properties of light and also the particle-like properties of light. And I'm just quoting a couple of results here on this slide. Upstairs here, this is work that was done by a famous scientist, like more than probably 150 years ago, maybe more than that, called Young. And he showed that light exhibited interference, a property we call interference. And the only way of understanding interference is that light is waves. We see interference with, say, water waves, ocean waves. We see interference with sound waves. And so seeing interference of light indicated it was a wave. But at not too dissimilar time, Heinrich Hertz, conducted experiments where he showed that light exhibited properties that were particle-like. And actually, he observed the collisions of light with electrons. And these collisions looked like light was a particle colliding with an electron, a particle, and bouncing off one another. And so in the history of the experiments to uncover the nature of light, there were both experiments that showed it could exhibit particle-like properties and wave-like properties. Finally, this is a slide on our modern understanding of light. What do we really think light's a wave? Do we really think light's a particle? We actually think today that it's more complicated than light being a particle or light being a wave. Light is something that exhibits both particle-like and wave-like properties. That's why we call think of light as having this dual wave-like, particle-like nature. And it was Albert Einstein who first argued the case that light has both particle and wave-like properties. He called a particle of light, a kind of a packet of light, the smallest packet of light. He called that the photon, right? You've probably heard of that term, the photon. And photons carry with them a certain amount of energy. Each photon has a characteristic energy that depends on the frequency of the light. And this equation, this famous equation from Einstein, represents really the relation between the particle-like characteristics of light, so photons of light carrying a certain energy, and the wave properties of light, waves of light having a characteristic frequency. And this constant h between that kind of energy particle-like perspective and that frequency wave-like perspective, that constant h is called Planck's constant. And its size, I've written it down here, is tiny in these units, 6.6 times 10 to the minus 34 joules seconds. Look, if you've done chemistry, I'm sure you've done chemistry, you've been had to go through that ordeal. If you've done chemistry, you know Planck's constant. Look at the units of Planck's constant. Joules seconds. So over here, for frequency, describing the wave-like nature of light, we got something in inverse seconds. Over here on the left, energy, something describing the particle-like properties of light, we got something in joules. So our Planck's constant takes us from the wave-like properties to the particle-like properties and converts the units from hertz or inverse seconds into joules, the units of energy. And so this equation, this simple little equation, is really the bridge between these Joule natures of light, between the particle-like properties and the wave-like properties. Okay, that was topic one. You'll be relieved that the history lesson is over, I'm sure. And now we're going to move on to discussing what we call geometrical optics, what we call ray optics. And within geometrical optics, ray optics, we're going to discuss the propagation and, most importantly, the reflection and the refraction of light. So that's our target for the remainder of the class. What do I mean when I say geometrical optics? What do I mean when I say ray optics? Well, what I mean by geometrical optics, ray optics, is sketched in this overhead. What I mean is that we can treat light, whatever it is internally, whether it has wave-like properties or whether it has particle-like properties, or in reality that it has Joule properties, we can treat it as rays traveling in straight lines. And so geometrical optics, ray optics, is about the world, the domain in which we can treat light rays or other electromagnetic waves as just traveling as rays in straight lines. So these light rays, I drew a few examples over here on the right-hand side. Those light rays show the direction of propagation. So here's a light ray that's traveling from the left to the right. Maybe there's a flashlight over here producing these light rays. It's a really bad flashlight drawing, but maybe there is a flashlight over there producing those light rays, and they're traveling from left to right. At any particular location here, we call this flood of rays, or here, we call the rays at each of these planes, we call those planes the wave front. And actually on each of those wave fronts, those light waves or those electromagnetic waves would all have the same amplitude, they'd all have the same phase. They're oscillations, they're sinusoidal oscillations of their electromagnetic fields, would all have the same phase, all have the same amplitude. Okay, so turns out that this approximation, this ray approximation, is sometimes good. You can apply ray optics, and it's sometimes not good. You can't apply ray optics. And the condition for it being good or not being good amounts to the comparison of the scale of your mirrors or lenses or optical equipment compared to the scale of the wavelength of the light or electromagnetic wave. So in this bullet, I called D, right? That's the dimensions, that's the scale in meters of your mirror or your lens or your optical equipment. I called lambda. That's the That's the wavelength of the light that you're illuminating your mirror, your lens, your optical equipment with. And ray optics, the ray approximation, is good when d is much greater than lambda, when the dimensions of the mirror of the lens are much greater than the wavelength of the light. Now, if you think about visible light and you think about your average mirror or lens, right? You know, your average mirror or lens is the scale of centimeters or meters in size. So D would be centimeters or meters. The wavelength of visible light, if you remember, runs from, I'll never forget this, it runs from about 400 nanometers to about 700 nanometers. Nanometers 10 to the minus 9 meters. So obviously for visible light of 400 to 700 nanometers, that's much, much smaller than the dimensions of your lens, your mirror, your optical equipment. So for visible light, ray approximation, ray optics is a good approximation, an excellent approximation. Ray optics, the ray approximation, isn't good if you think about radio waves. They're also electromagnetic waves, but if you recall, radio waves, depending on, I don't know, whether it's FM radio or AM radio, if they still have that, their wavelengths are meters or tens or hundreds of meters. And so if you've got wavelengths of tens of hundreds of meters, then devices like mirrors or lenses that were centimeters or meters, well, that size scale is not bigger than the wavelength of radio waves. It's smaller than the wavelength of radio waves. And so the ray approximation would collapse. Ray optics would collapse for radio waves. So we're talking about visible light. We're not talking about radio waves here. Okay, so the first rule that we're going to discuss of light, we're going to discuss propagation, reflection, refraction. The first rule for the propagation of light is a really very simple rule. It says that if light rays travel from some initial location to some final location, and on here, that initial location is labeled P over here on the left, final location Q over here on the right. Light travels in a straight line from P to Q if it's traveling through uniform material, traveling through the same material. It just travels in a straight line. Now, the comment that it travels through uniform material is an important qualification about propagation of light. If the material was non-uniform, then it would not necessarily travel in a straight line. And a classic example of that is when the sun sets or when the sun rises. If you ever go, next time you go out and you think, oh, I'm going to look at the sunrise, I'm going to look at the sunset. You see the sun come up over the horizon, or you see it float down below the horizon. You'll notice that the sun, which is a sphere, the sun's shape gets distorted as it's rising at sunrise, or it's setting at sunset. It gets distorted, and it's because the light is traveling through the atmosphere, and the atmosphere in the direction of the horizon, whether the sun is rising or setting, is not just uniform. And so that distorts the path of the light rays. It distorts the shape that we see the sun. So the law of propagation of light, that light rays travel in a straight line, only applies if the medium, material, matter they're traveling through is a uniform material. Okay, Law of reflection. And here you see in this slide a nice example of reflection of the mountain in the distance here reflected in the lake in the foreground here. And we see an image of the mountain in the lake here from reflection. So the law of reflection is sketched here. So in this sketch, there are a few important things. This horizontal line is the boundary between two different materials, two different media, two different optical media. So in this case of this picture, this would be air upstairs here, and this would be water downstairs here. This vertical line, this is a line, a special line, it's an important line, is what we call the normal to the boundary. So it makes an angle of 90 degrees. Here's a 90-degree angle to the boundary. And it's a line that we use as a reference point. We use it as a reference point to describe the angle of the incident light and the angle of the reflected light. So look, over here on the left is a light ray that's heading towards the boundary or the interface between the air and the water. And over here on the right is a light ray that's emerging after reflection from the boundary or the interface between the air and the water. And when we describe the direction of the incident light ray, when we describe the direction of the reflected light ray, we measure those angles that describe the direction with respect to the normal. So if I want to tell you the direction of the incident incoming light ray, I'll tell you theta I, measured from the normal here. If I want to tell you the angle, the direction of the reflected light ray, I'll give you the angle with respect to the normal here. Okay, so that's the picture that's going to allow us to describe the reflection of light, the law of the reflection of light at some boundary like this air-water boundary. And the law of reflection is simple. It's stated here. It's simply that the reflected angle is equal to the incident angle. So if that incident angle was 30 degrees to the normal, then the reflected angle is 30 degrees to the normal. If it was 50 degrees to the normal, reflected angle is 50 degrees to the normal. This law has been known for thousands of years. So that's why I stuck up here. It was quickly discovered by mankind. Now, to be precise, this is the law, what we call specular reflection. It is not the law for what we call diffuse reflection. So specular reflection is when the incident light, angle theta I, is reflected at the same angle theta R after reflecting, bouncing off the surface. In diffuse reflection, incident light, angle theta I, is reflected at many angles. It bounces off at many angles from the surface. So this law is for specular reflection. Here's a picture, a left and a right on this picture, that is suggesting, showing you kind of the difference between specular and diffuse reflection. So on the left-hand side, we got specular reflection, when the light of the headlights of the truck is reflected off the the wet road surface. You tend to see specular reflection there, where the angle of incidence equals the angle of reflection. So this is specular. Oops. On the other hand, on dry road surface, right, the light is reflected off the road surface again. You see the color of the light in the road surface, but it's reflected in many directions. So this is diffuse reflection. And so that's an example of the difference between the two. Difference between reflection of a wet road surface of a dry road surface is roughly the difference between specular and diffuse reflection. Okay, now law of refraction at boundaries. Let's introduce that. So law of reflection was only discovered some hundreds of years ago compared to law of refraction that was discovered thousands of years ago. So there's a much more recent history to the discovery of refraction compared to the discovery of reflection. And the law of refraction is more complicated than the law of reflection. And so that's part of the reason. It also needed some mathematics to describe the law of refraction that you didn't need for the law of reflection. So that's also part of why it was a later discovery. This sketch is how we describe refraction. So again, there's a horizontal line in this sketch. And that horizontal line in this sketch is the boundary between the two different media, the two different optical media. So in the last example, it could be air and water again. Or it could be water and air, or it could be glass and air, or air and glass. So there's lots of possibilities here, two different optical media. The vertical line again, didn't really draw that in the right place. Let's try and do better. That vertical line again is the normal to the boundary. So again, the normal is a reference point, and normal means 90 degrees to the surface, right angle to the surface. And again, we use that normal as the reference point for measuring the directions of the incident rays, the incoming rays, and the refracted rays, the outgoing rays. Now, in the case of reflection, when you got reflection from air to water, the light ray comes in from the air side and is reflected back into the air. When you got refraction, the light ray comes in from the air side and is refracted, bent into the water. So here the light ray actually travels from one material to another material. In reflection, the light ray stays in the same material after bouncing off the other material. So here comes in a light ray from the left, this location P, and it heads down over here towards this location Q. And this is the direction, theta I, of the incident light ray. And this is the direction with respect to the normal, theta R, of the refracted light ray. And so we want to know the law of refraction is about the relationship, the connection between the theta I and the theta R of the incident and the refracted light ray. Now, it involves two new quantities. These are just numbers. Ni and Nr. Ni is a quantity that describes the optical properties of, in this case, the air. Nr is a number that describes the optical properties of the other material, in this case, the water. And they're called refractive indices. So this is the refractive index Ni of the incident medium. This is the refractive index Nr of the refracted medium. And they describe the two different media. So air, water, glass, plastic have different refractive indices because they're different materials. The law of refraction says that if you multiply the sine of the angle in the incident medium, so sine theta, by the incident refractive index, that's equal to the product of the sine of the angle in the refracted medium, so sine theta r, times its refractive index. And so that's this equation here. Look, it's the same product on the left-hand side and right-hand side of the equal sign. In both cases, it's the product of a refractive index and the sine of an angle. In the left-hand side here is the refractive index for the incident medium and the sine of the angle of the incoming ray. And on the right-hand side is the refractive index of the refracting medium and the product with the sine of the angle of the light ray in the refracted medium. Now that's the law of refraction. Again, I should qualify it. The law of refraction, this law of refraction is for what we call specular refraction, where that incoming light ray is refracted at a certain angle. There's also diffuse refraction in circumstances. In that case, the incoming light ray is refracted at a variety of angles. So this is the law of specular refraction. Now, one final comment here. In our sketch shows the light ray bent towards the normal. And by that, I mean that the incident angle is bigger than the refracted angle. That happens when you travel from lower refractive index to higher refractive index. And air to water is an example of that. If the light wave was traveling from the water to the air, the light ray will be bent away from the normal. And that happens when you travel from higher refractive index to lower refractive index. So this law of refraction is great because it has both capabilities built into it. If you're traveling from lower to higher refractive index, you get bent towards the normal. If you're traveling from higher to lower refractive index, you get bent away from the normal. That's all built in that one law of refraction. It's called Snell's law, obviously after the scientists that discovered it. Okay, I want to show you a few properties of light in matter. In the last class, we were really talking about light in vacuum. In this class, we're focusing now on light in matter. So, important point here. The speed of light in empty space, the speed of light in vacuum, is 3 times 10 to the 8 meters per second. That's what we give the symbol c to. The speed of light in empty space, the speed of light in vacuum. The speed of light in matter, so that could be the speed of light in air, could be the speed of light in water, could be the speed of light in diamond. That's smaller than the speed of light in vacuum, the speed of light in empty space. And the amount by which it's smaller, the degree by which it's smaller, is the refractive index n of that particular material. And so this equation here, this is important. The speed of light in a material, that's the v, equals the speed of light in vacuum, that's the c, divided by the refractive index of the material. So if you want the speed of light in air, you've got to divide the speed of light in vacuum by the refractive index of air. If you want the speed of light in diamond, you've got to divide the speed of light in vacuum by the refractive index of diamond. And here's a table. I stole it from the book without asking them. Here's a table of different refractive indices of different materials, of optically important materials. So I'll just point out a couple of them. Look at air down here. So air's refractive index is very, very, very close to 1, but not exactly 1. So it's 1.0003. So it's just fractionally greater than 1, which means that the speed of light in air is just fractionally smaller than 3 times 10 to the 8 meters per second. And so light does travel slower in air, but only by, the scale of parts in 1,000. Here's ice and water. Okay, ice and water are transparent to light, to visible light. Light traveling through ice and water travels slower than light in vacuum. And for liquid water, it travels slower by a factor that's about 1.33. So it's something like only 2 times 10 to the 8 meters per second, not 3 times 10 to the 8 meters per second. And also in ice, light travels slower, and it's by a factor that's about 1.31. So again, it would be about 2 times 10 to the 8 meters per second, not 3 times 10 to the 8 meters per second. So light travels somewhat slower, significantly slower in ice and water. In diamond, I don't have any diamond, but I know somebody that does. In diamond, the refractive index is 2.4. It's one of the largest refractive indices that we know. And that means that light travels much slower in diamond, more like 1 times 10 to the 8 meters per second. And it also means that light, when refracted by diamond, when bent into diamond or leaving diamond, is bent at large angles. So that's why diamond is so special. Diamond can trap light, contain light, because it's hard for the light to get out. That's why it gives diamond those special characteristics, special properties when you look at it. Okay, that was the speed of light in different materials. This slide looks at not just the speed of light in different materials, but also the wavelength of light and the frequency of light. And specifically, I want to imagine light traveling from one medium to another medium again. So if you look at this sketch, this is the incident medium in gray. Called its refractive index here, called it N1. And this is the refracted medium, N2, call it refractive index N2. So light is traveling downwards from the incident to the refractive medium, from this top to this bottom medium. And we're just going to walk through, what happens to the speed, what happens to the wavelength, what happens to the frequency, all those characteristics that we use to describe light. Okay, so the starting point, right, is we're moving, the light is moving. We can imagine we're the light. We're traveling from medium 1 to medium 2. Medium 1 is described by refractive index N1. Medium 2 is described by refractive index N2. There's no reference to whether N1 is bigger than N2 or N2 is, or N1 is smaller than N2. So light will change its speed when it travels from the upper medium to the lower medium in general. It will change its speed because the speed in medium 1 is the speed of light in vacuum divided by medium 1's refractive index, and the speed in medium 2 is speed of light in vacuum divided by medium 2's refractive index. And so if n1 and n2 are different, the light changes its speed. The light also changes its wavelength. So when light travels from medium 1 to medium 2, the wavelength of the light in medium 1 is the wavelength of the light in vacuum divided by the refractive index of medium number 1, and the wavelength of light in medium 2 is the wavelength of the light in vacuum divided by the refractive index of medium 2. And so again, if n1 and n2, the two refractive indices are different, the two wavelengths are different. So not only does the speed change when light travels from one medium to another, slows down or speeds up, depending on who's the bigger, who's the smaller refractive index. But the wavelength also changes. The wave stretches out, the wave shrinks down, depending on who's the larger or the smaller refractive index. But interestingly, the frequency doesn't change. The frequency of this light ray is the same in vacuum, same in medium number 1, same in medium number 2. F1 equals F2 equals F, the frequency in vacuum. And so these are three important statements about what happens to the speed, what happens to the wavelength, and what happens to the frequency when light travels from one medium to another. The changes are all related here. The ratio of the speeds is equal to the ratio of the wavelengths, which is equal to the inverse ratio of the corresponding refractive indices. And so this is telling you that if n1 was smaller, closer to 1 than n2, then the speed in n1 would be larger. And the wavelength in n1 would be larger. And the speed in n2 would be smaller, and the wavelength in n2 would be smaller. And that's what's shown in this picture, right? The speed is bigger in the top region, refractive index n1, smaller in the bottom region. The wavelength is bigger in the top region, refractive index 1, smaller in the bottom region, refractive index n2. Okay, I wanted to make this demonstration of shining laser light onto a glass block and videoing the reflected and the refracted rays. But I'm afraid I completely failed with this demonstration. I don't understand it. I could see it. I could see the refracted ray. I could see the reflected ray, but the camera on my laptop did not see it. Could never get it to see both the reflected and the refracted ray. So we're going to have to, after all those apologies, we're going to just have to look at this picture, I'm afraid. So this shows you, I'm going to change the color of this pen. Here comes the incident ray. No, it doesn't. Try again. Here comes the incident ray. And it's moving through air, and it's going to strike this glass block here. So that's ray number 1, the incident ray. Now, when it strikes the glass block, in reality, two things in general happen. There's reflection. And so here's the reflected ray. That's ray number 2. And as we know, right, that's described by the law of reflection. That's where these two angles, measured with respect to normal, are equal to one another. Theta incident equals theta reflected. Then there's a refracted ray. Here it is. And that's the ray that gets bent as it travels, deflected as it travels from one medium to another medium. And this is the angle of refraction. And it's the law of refraction that describes the relationship between the theta I and the theta refracted in this new material here. And so this picture shows you actually, and I wish the demonstration had shown you, that you can actually have, so you actually have in general simultaneously both reflection and refraction. When you look through a window, I'm looking through the window at my office right now, there's reflection and refraction of the light coming into the window. Some of it's bouncing off the window. Okay, on the last slide, what is the wavelength in the numerator? What is the wavelength? You're wondering what I'm doing now. I'm reading something from the chat just to explain it. On the last slide, what is the wavelength in numerator in the equation? Wavelength 1 equals wavelength of an index of refraction 1. Is it the original wavelength of the wave in question? Let me go back. Let me clear this guy. And then try and go back to confusion. Okay, so I'm thinking the question is about who is, gosh. What's this wavelength? What's this wavelength? Lambda is the wavelength in the vacuum. And actually, Emily has already answered this before I could even get to it. Lambda is the wavelength in the vacuum. Lambda 1 is the corresponding wavelength in the material N1, and lambda 2 is the corresponding wavelength in the material N2. So lambda with no subscript in the vacuum, lambda with a subscript 1 in material 1 with refractive index N1. Lambda 2 is the wavelength in material 2 with refractive index N2. Okay, now let's turn to some examples and illustrations. We better get that done. Okay, go quiz questions. Okay, I think our time is up. So this is a ray that is bent towards the normal. And when a ray is bent towards the normal, that's the signature of a ray that's traveling from lower refractive index to higher refractive index. So an example for this ray might be from air to water or air to glass. When a ray travels from higher refractive index to lower refractive index, so that would be from, say, water to air or glass to air, then it's bent, that's bent away from the normal, so that the refracted angle would be larger. So the way Snell's law works, the way the law of refraction works, is that if you travel into higher refractive index, you get bent towards the normal. If you travel into lower refractive index, you get a bent away from the normal. This is a famous example for lifeguards, actually. I'll just tell you the lifeguard story here. So if you're a lifeguard, and you're standing here on the beach. So medium number 1 is the beach, the sand. And you want to rescue the drowning person in the ocean. So medium number 2 is the ocean. Well, supposing you're a lifeguard that's taken physics 213, you'll know, if you're a lifeguard taking physics 213, that you don't want to take the shortest path to get to the swimmer, the drowner. And you don't want to do that because you may be a good swimmer, but you can run faster on the sand than you can swim in the water. So it's advantageous for you to travel further on the sand and less far in the water. So you would run along the sand, taking a little extra trip along the sand to cut down your journey in the water. That's because you go faster on the sand than you go in the water. And that's what light does. That refraction is the exact amount of refraction that you need for light to get from on the shore to in the water in the shortest possible time. It travels a little extra time in medium 1, a little less time in medium number 2, shortening the overall time. Oh, there's a fantastic question in the chat. How does light increase its speed when it leaves a material? Yeah, that's a really, really great question. And so the point is, you might say, well, look, light goes into a material, it decreases its speed. It comes out of the material, it increases its speed. You might say, well, look, that's changing its energy. Well, maybe it's okay to lose a bit of energy, but it doesn't sound okay to gain a little bit of energy. So I can partly answer this question for you. Think back to that famous Albert Einstein equation, that E equals Planck's constant times F. The light ray's frequency stayed the same when it traveled from one medium to another medium. The wavelengths changed, the speed changed, but its frequency stayed the same. And its frequency determines the energy of the photons. And so, although the light ray does speed up and slow down when it travels from one material to another material, the little photon packets of light don't actually change their energy. So maybe that makes it more believable, that you're not increasing and decreasing the energy, getting the energy from somewhere, destroying the energy. Rather, the energy is actually staying the same. Okay, I want to look at an example of reflection and then an example of refraction. This takes us back to 1969, if I can remember. And this was the first lunar landing, 1969. And this is Neil Armstrong walking on the moon. And it looks like these are his suitcases, right? But they're not his suitcases. He's not going to sleep or stay on the moon hotel. These are called retroreflectors. And he left these retroreflectors on the moon. And they're basically little boxes containing mirrors. And back here on Earth, since Neil Armstrong left his retroreflectors on the moon, we've been shooting laser beams at the retroreflectors and watching the reflections of the laser beams come back to Earth. And we've learned some interesting things by reflecting light off the retroreflectors on the moon. We've learned that the moon is spiraling away from us. It's not going around in the same circle every month. That circle is getting larger and larger and larger. Now, it's not by much. It's increasing by a few centimeters a year. But we've learned that the moon is actually, the orbit of the moon is slowly swelling up, and the moon is slowly separating from the Earth. And we learned that from the retroreflectors. Now, this question is about these retroreflectors, how they work. And so the principle of the retroreflector is that you shine a light ray at it, and wherever you strike the retroreflector with the light ray, it reflects it directly back at you, i.e., the incoming light ray is deflected by 180 degrees. It's just sent back in the opposite direction. And so we're going to prove here with the law of reflection that the incoming light ray is reflected back at 180 degrees. And so here's the little picture that I'm going to use to solve this problem, to show you this effect. Here's the little picture. So imagine this is Neil Armstrong's retro reflector on the moon. Here comes the incoming light ray. It bounces off one of the two mirrored surfaces, obeying the law of reflection. It then strikes the other mirrored surface, again obeying the law of reflection. And then here's the outgoing light ray. And we're going to prove that there's 180 degrees between the incoming and the outgoing. So that if you're back on Earth, you fire your laser beam, right, at the retro reflector, bam, that laser beam comes straight back to you. And so here I'm going to calculate the deflection of the light ray as it comes in, bounces once, reflects once, bounces a second time, reflects a second time, and heads backwards. And so we're going to calculate the deflection. I'm going to call that deflection angle. It's a number of degrees. I'm going to call it delta. So think of delta as the total change in angle of the outgoing light ray compared to the ingoing light ray after the two reflections that occur for the incoming light ray as it becomes the outgoing light ray. And there's two pieces of information that we're going to base our solution to this problem on. And one is the law of reflection. So I've written that down here. So there's a reflection on this horizontal mirror here. And the law of reflection says that the incident and reflected angles are the same. So that's this equation here. And there's a reflection on this vertical mirror here. And the law of reflection says that those incident and reflected angles are the same. And I've denoted the second reflection as the angles by these primes. And so that's that second law of reflection here. So that's the law of reflection. I'm going to use that in solving this problem. And then I'm also going to use this little piece of geometry here. So when I drew this picture, I made a right angle triangle. There's a vertical side here. There's a horizontal side here. And there's a hypotenuse that's this sort of intermediate ray between the incoming and the outgoing rays. And together, the horizontal, the vertical, and the intermediate ray form a right angle triangle, right? This is a right angle between a horizontal and a vertical line. And well, if that's 90 degrees, and if there's 180 degrees in a triangle, then it must be that theta r downstairs here in the right angle triangle and theta I prime upstairs here in the right angle triangle must add up to 90 degrees. So those two angles, whatever they are, I don't know what they are, but they must add up to 90 degrees. I do know their sum. And so that's this second equation here. And with just that information, what I'm going to show you is that the light ray is always reflected backwards at 180 degrees. It's always sent backwards in the opposite direction. Always sent backwards in the opposite direction, no matter what that initial angle theta I is. That could be 1 degree, it could be 89 degrees, it could be 45 degrees, whatever it is, 1, 45, 89 degrees. The reflected light ray goes back in the opposite direction. So let's see how that works. So what we're going to do is calculate the sum of the two deflections. There's a deflection down here at the first reflection, and there's a deflection up here at the second reflection. reflection. It's the amount that the light ray is deflected, its direction is changed at this first reflection, reflection number one, and the amount that the light ray's direction is changed at the second reflection. That's reflection number two. Okay, so that's the theta 1 and theta 2, the two deflections. This is theta, sorry, that's the delta 1 and delta 2, the two deflections. Well, how big is this deflection? I've drawn it here in red. How big is it? Well, it's 180 degrees all the way around here, less the number of degrees consumed by theta I and theta R. So delta 1 is 180 degrees less the angle here. That's this amount of angle. And likewise, delta 2, this deflection is the full 180 degrees all the way around here, less the amount that's consumed by theta I prime and theta R prime in here. And so that's delta 2. And so I just plug in, oops, that's the wrong way around. Let me change that. I'm just going to plug in theta 1 here. I don't know why I can't do this. Here we are. That's plugging in theta 1. That's delta 1. And this is plugging in delta 2. I plug those in. When I plug them in, I did a couple of things, a little bit of rearranging. I saw I got 180 degrees here and 180 degrees here, so it's 360 degrees. That's not hard. I eliminated theta I. I replaced it with theta R because they're the same. So this is actually, here is minus 2 theta R's. And I also, over here, I eliminated theta R prime. It's the same as theta I prime. So this is equivalent to minus 2 theta I primes. And so that allowed me to rewrite that subtraction of these angles in terms of just two of the angles. And I wrote it in terms of theta I prime and theta R. And I did that because those are the two angles that I know add up to 90 degrees. So this little sum of the refracted angle at the first reflection and the incident angle at the second reflection, they add up to 90 degrees. And so I can just replace this by 90 degrees. And that's what I did down here. And so I've got 360 degrees minus 2 times 90 degrees. That's 180 degrees. It doesn't matter. This is fantastic. This is the fantastic thing about retroreflectors. It doesn't matter what this angle of incidence was, theta I. You always are reflected by 180 degrees. So that's fantastic. Okay, I want to give you an example of refraction now. So the second and last example. So here's an interesting phenomenon. It's best to try this with moonlight. Don't do this with regular old sunlight. But if you were to look around the moon at night, or with a special device, look around the sun during the day, you'd see that not only would you see in the center the moon or the sun, but you'd see a ring, a circle around the moon or the sun, an angle of 22 degrees. Where does that circle around the moon or the sun come from at this angle of 22 degrees? Here's a picture of it, right? In the center here, is the sun. And see this circle, this ring? Where does that come from? Well, it comes in the following way. So you actually see light from in this picture, you're seeing light from the sun that comes to you directly. So in the center here, this is light coming directly to you from the sun. But you also see light that's refracted, bent by 22 degrees, that comes to your eye from this circle, or this arc, that is 22 degrees away from the sun. And that's due to refraction. And it's due to refraction of something that litters the sky. It's ice crystals that litter the sky, and they act like little prisms, and they refract or bend the light rays and cause this ring around the sun, cause this ring around the moon. And it's at 22 degrees. And so we're going to explain that 22 degree halo that you can see around the sun, that you can see around the moon. So this sketch here is how you get the 22 degrees. And that's what I'm going to show you with the law of refraction. So let's see if we can understand how this works. Oops, sorry. See if we can understand how this process works. So you get the 22 degrees bending of the light rays when light strikes ice crystals in the atmosphere and is bent by those crystals. And those crystals form little prisms. Here's an ice crystal in the atmosphere, and there's 60-degree prisms. And the minimum bending of this light ray, when it strikes this prism, is when the internal light ray travels parallel to the prism surface. So this is the geometry for 22-degree refraction. And this, we'll see, will give you this 22-degree deflection of the light ray. And it comes about from a deflection of 11 degrees at the surface where the light enters the crystal, and another 11 degrees where the light leaves the crystal. And so let's see if we can understand how this works. First, I got to see if I can understand how this pen works. Okay. On this slide, I'm going to show you that when the light enters the ice crystal, enters the prism, it gets bent by 11 degrees, more precisely 10.9 degrees. On the next slide, I won't go through the next slide in detail. It shows you that the light gets bent by another 11 degrees or 10.9 degrees on the journey out of the crystal. So you get a deflection over here on the left of 11 degrees, you get a deflection over here on the right degree of 11 degrees. How do we get this deflection? Well, look at the geometry here. So here comes in the light ray. It's at some angle to the normal. We don't yet know this angle. It's refracted towards the normal because it's traveling into ice that has a greater refractive index. And this angle here, from the 60-degree geometry of the prism, that angle of refraction, that's 30 degrees. You can see that that's 30 degrees because there's 60 degrees here. This is a right angle. And so that there's only 30 degrees left here. So the angle of refraction is 30 degrees when the light ray enters the ice crystal. Well, think about the law of refraction. written it down up here. The law of refraction relates the incident and refracted angles to the two refractive indices. We know the refractive index of air. We know the refractive index of ice. We know the angle of refraction, 30 degrees. The only thing we don't know is the incident angle. And so we can turn this equation around to solve for the incident angle. That's what I did here. And I find it's 40 degrees. So the light ray comes in at 40.9 degrees and then gets bent to 30 degrees. That means it got deflected by the difference between them, 10.9 degrees. So there's 10.9 degrees of deflection when the light ray goes in. And there's also 10.9 degrees of deflection when the light ray comes out. And I figured that out on this slide here. I won't go through this slide because it's exactly the same calculation, but it's for the outgoing light ray at the right-hand face rather than the incoming light ray at the left-hand face. But you get another deflection of 10.9 degrees there. And again, you get it by the law of refraction. Well, so now we can put those two things together. Oh, sorry. Maybe. Now we can put those two deflections together, and 11 degrees over here on the left, 11 degrees over here on the right, you get 22 degrees in total. And that's why you get the 22-degree halo in the sky. So when you look in the sky and you see these halos, that's indirect light that's coming to you, and it's coming to you in this amazing way. It's coming to you through the refraction of the light ray by little ice crystals, tiny ice crystals that are littering the sky. And they tend to refract by this minimum amount of 22 degrees, and you get this ring around the sun, you get this ring around the moon, you get these halos around the sun and the moon. So that's another natural example of the phenomena of refraction, the bending of light rays. Anyway, let me finish there. I'm sorry I've gone over a couple of minutes. We talked about the dual nature, particle light, wave-like nature of light. And then we talked about the propagation, reflection, and refraction of light. We gave some equations describing reflection and refraction and how speeds and wavelengths, etc., change. And then we looked at a couple of examples, the retroreflectors for an example of reflection, and the moonlight, sunlight halos as an example of refraction.